Hello everyone, I am Dr. Krishna Sarker. Here in this session, I will be going to discuss about block diagram reduction rules and definition of basic elements of block diagram. This is linear control systems, lecture series on linear control systems, lecture number 22. So our topics, block diagram reduction rules and definition of basic elements of block diagram. Next, overview. What is overview? Block diagram reduction technique. First point, block diagram reduction techniques. And rules number 1, block diagram reduction for open loop systems. Rules number 2, cascade connection of blocks. And rules number 3, parallel connection of blocks. Rules number 4, shifting a summing point after a block. Rules number 5, shifting a summing point before a block. And rules number 6, shifting a takeoff point after a block. Rules number 7, shifting a takeoff point before a block. Rules number 8, shifting a summing point before a summing block. And rules number 9, shifting of takeoff point after a summing block. Rules number 10, represent rearrangement of summing point. Rearrangement of summing point. And overview, next overview, rules number 11, negative feedback closed loop control systems. Rules number 12, positive feedback closed loop control systems. And rules number 13, positive negative feedback control systems. Rules number 14, unity positive negative feedback control systems. And procedure for reduction of block diagrams. Rules number 11, 12, 13 and 14 already discussed in lecture number 18, 19 and 20. Then basic elements of block diagram. What is the basic elements of block diagrams? Basic elements of block diagrams are blocks. Number 1, blocks, summing points, takeoff point. Number 4, arrows. And number 5, forward path and feedback path. Number 6. So R of S, this is the reference input or excitation. And this excitation always positive. And this is the summing point with cross. And E of S is called the actuating signals or error signals. And G of S is the planned gain or system gain. And C of S, controlled output or effect of the systems. And this is the feedback information, feedback for better quality of the output. And H of S is the feedback element. B of S is the primary feedback gain. And this is the negative. So this is the negative feedback. And this is the canonical form of a feedback control systems. And G of S or this block, this is the number 1 point block. This is the block. And number 2, this is the summing point with cross. And this is the takeoff point. This is the takeoff point. And this is the arrow, forward path direction or forward path direction. And this is the feedback path direction. This is the feedback path direction. So this is the forward path direction. And this is the output to input. This is feedback path, and input to output. This is the forward path direction. Then our main target, rules number 1, block diagram reduction for open loop control system or open loop systems. So R of S, this is the reference input. This reference input may be step, ramp, parabolic impulse, sinusoidal, analog, digital, any type of input you can apply. And this is also cause of the system or cause of the physical systems. This is the block gain or block G of S or planned gain. This is the control. C of S is called the controlled output or excitation. This is not controlled output or effect of the systems. Next, this is block diagram for open loop systems, where R of S equals to reference input or controlled variable. This is also called cause of the system, excitation of the system. C of S is called controlled output or controlled variable. G of S is called forward path transfer function. Transfer function G of S, this is the G of S or planned gain, equals to C of S by R of S. What is the definition of transfer function? Laplace transform of output divided by Laplace transform of input, and all initial conditions are zeros is called transfer function. So this is the Laplace transform of output divided by Laplace transform of input, and the output of the systems is C of S, and this C of S equals to product of the forward path gain G of S and the input or excitation R of S. This is the output of the system. C of S equals to GS into R of S. Then example 1, block diagram reduction technique. Example 1, block diagram reduction for open loop systems. Determine the transfer function of the block diagram shown in figure A. R of S reference input, and this is the system gain C S plus 5 by S square plus 19S plus 13, and C of S equals to controlled output. So what is the open loop transfer function? This is the block diagram for open loop systems. The overall transfer function G of S equals to C of S divided by R of S, and G of S equals to what? G of S equals to C of S by R of S equals to S plus 5 by S square plus 19S plus 13. So this is the block diagram reduction for open loop systems. For these systems, CS by RS equals to S plus 5 by S square plus 19S plus 13. Then block diagram reduction technique. Rules number 2, cascade connection of block diagram. This is also very important. R of S equals to reference input. R of S equals to reference input, and first planned gain or block gain equals to Z1S, and the first output C1S, C1 of S, and C1 of S output input of the Z2S second block, and Z2S output signal equals to C2S, and this is the input of Z3S, and overall output ultimate C of S. So calculate CS by RS equals to transfer function. Calculate CS by R of S, CS by RS, and this configuration actually series configuration or cascade configuration. This is the forward path, only forward direction signal passing to only forward direction. Then figure A, block diagram in cascade. Figure A shows output is cascade connection of 3 blocks, in which the output of block 1 connected to the input to the of the block 2. So this is the very important output of block 1. This is the block 1. So output of the block 1 connected to the input of the block 2. Input of the block 2, also output of the block 2. This is the output of the block 2 connected to the input of the block 3, connected to the input of the block 3. Then calculate CS by RS connected from figure. This is the output for first block. C1S is the output. So what is the transfer function? Output C1S divided by R of S, divided by R of S. This is the for first block. This is for first block. C1S by RS equals to G1S. Similarly, for second block, C2S by C1S equals to Z2S. And for third block, CS by C2S, because C2S is the input of the Z3S. So CS by C2S equals to Z3S. For first block, transfer function C1s by Rs, and for second G2s, C2s by C1s, and for the third G3s equals to CS by C2s. This is the cascade block diagram, and C1s by Rs equals to this G1s, C2s by C1s equals to G2s, and CS by C2s equals to G3s, already discussed. And then multiplying equation 1, 2, and 3, and we get G1s into G2s and G3s. First right hand side multiplication, G1s, G2s, and G3s. This is the G3s. This is the G3s. Then right hand side multiplication, first C1 by Rs into, this is into C2s by C1s, C2s by C1s, and third point into third point CS by ultimate C2s. So what is the transfer function? Output by input. In this case, C1s cancel and C2s cancel. So only CS by Rs is the output of the system. And this is equivalent to CS by R of S. Then multiplying both sides, G1s, G2s, G3s equals to C1s by Rs into C2s by C1s into CS by C2s. And this is equivalent to CS by Rs, already discussed. Then CS by Rs equals to what? G1s, G2s, and G3s. Product of the first block, second block, and third block gain. And R of S equals to G1s into G2s into G3s, and the output equals to C of S. So C of S output divided by R of S equals to G1s into G2s into G3s. We concluded that the cascade connection of 2, 3, or n blocks can be replaced by a single block whose transfer function is equals to the product of the transfer function of individual blocks. So cascade connection of the blocks, Determine the transfer function of blocks diagram shown in figure A. This is the cascade connection. Example 2. This is example 2. First input equals to R of S, and transfer function or gain equals to S plus 11 by S plus 13, and the first block output C1s. And this is the input also second block, and second block gain equals to S1 by S plus 14, and the second block output equals to C2s, and this is the input of the third block, and this is the transfer function or gain equals to 100 by S in S plus 17, and output C of S. Solution. This is example 2. The blocks in figure A are connected into cascade. The transfer function is CS by Rs equals to what? CS by Rs equals to G1s into G2s into G3s. Then first point, G1s equals to S plus 11 by S plus 13, and G2s equals to 1 by S plus 14, and G3s equals to 100 by S plus 17. Then multiply just S plus 13, S plus 14, S plus 17, and 100 into S plus 11. This is the transfer function by using cascade connection of the blocks. This is the solution. 100 into S plus 11 by S plus 13, S plus 14, S plus 17. Then parallel connection of blocks diagram. Parallel connection of the block diagram. This is the reference input R of S. First block G1s, and this is the comparator summing point, and this with cross, and this is the positive signal, and the output of the signal is X1s, and the output of overall output C of S equals to what? C of S equals to X1s equal only. And also X1s equals to what? X1s equals to G1s into Rs, because G1s equals to X1s by R of S. X1s by R of S. Second block G2s also connected by positive, and this signal gain equals to x2s. So add x2s, and third signal G3s, and this is the x3s, and this is a minus connection. So here minus x3 into s. The output C of s is the algebraic sum of signals x1s, x2s, and then x3s. So Cs equals to what? Cs equals to x1s plus x2s minus x3s. C of s equals to x1s plus x2s plus x3s. Since x1s equals to what? X1s equals to z1s into rs. And x2s equals to what? X2s equals to rs into z2s. And x3s equals to rs into g3s. Then cs equals to what? Put here x1s value, x2s value, and x3s value, rs into z1s plus rs into z2s minus rs into g3s. So cs overall transfer function, overall gain equals to this, and cs equals to just common r of s, g1s plus g2s minus g3s, and common r of s, and cs by rs equals to called transfer function. So already discussed this block. rs reference input, g1s, g2s, and g3s parallelly connected, and the c of s equals to x1s plus x2s minus x3s. So cs equals to g1s plus g2s plus g3s whole into rs. The overall transfer function, then what is the overall transfer function? Just cs by r of s equals to this function g1s plus g2s plus g3s. So for parallel connection, addition, and for cascade connection, multiplication of the gain. Multiplication of the gain. Then C of s by R of s, just output by input. C of s controlled output, write down here C of s, and this is the input or reference input. This is equivalent to G1s plus G2s plus minus G3s, G1s, and R of s reference input G1s plus G2s minus G3s, and the controlled output C of s. This is single block diagram where output equals to C of s and input equals to R of s, and C of s divided by R of s equals to G1s plus G2s minus G3s. If all the blocks have a connected input and overall output is the sum of individual output, then blocks are said to be parallel. Parallel connection of the blocks. So this is already discussed. RS reference inputs, G1s, G2s, G3s gain of the systems, and this is the R positive forward path, positive forward path, negative forward path, and this signal X3s. Then CS equals to RS equivalent circuit. This is the equivalent circuit for this parallel circuit. Equivalent circuit equals to R of S input and the G1s plus G2s minus G3s. For nth order parallel path, G1s plus G2s minus G3s plus dot 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 plus Gn of S. If all the blocks have a connected input and overall output is the sum of individual output, then blocks are said to be parallel. Parallel blocks can be replaced by a single block, and the transfer function is equal to the algebraic sum of the transfer function of the parallel block. So this is the basic idea of the parallel connection of the block. Then example 3. What is the example? Just this is the example. For first block, here 2 by s plus 3, second block 1 by s plus 1, and third block 1 by s. And the RS equals to reference input and CS equals to system gain. X1s for first forward path and X2s for second forward path, and X3s equals to third forward path. The overall output C of S equivalent circuit R of S equals to R of S input and Z1S plus Z2S minus Z3S, and the output equals to control output C of S. So solution, the blocks in figure A are connected in parallel. The transfer function is CS by RS. This is the CS by RS because overall transfer function C of S and the input equals to R of S. So output by input equals to first block plus second block plus third block. So this is the output by input ratio. Then overall or final transfer function 4s square plus 9s plus 13 divided by s into s plus 1 plus 13. This is the transfer function for example 3. Thank you.